Attends, ça, je le mets à ma ceinture.
Ouais, ça, tu l'accroches, tu le mets carrément dans la poche.
Là, comme ça?
Ouais.
Oui. Attends.
La poche, carrément.
Okay, so for this last talk of the morning session, it's a pleasure to introduce Thomas Duquesne from Sorbonne Université. He's going to talk about branching random walks on trees.
So, thank you, Gregory. So I will start my talk immediately switching to French for obvious reason, and just to wish a happy birthday to Jean. Donc, depuis le début de la conférence, j'ai été un petit peu étonné des introductions, notamment Nicolas Curien n'a pas dit grand-chose. Bon, voilà. Puis après, quand Wendeline a parlé de Jacques Dutronc, j'ai vu Grégory y pâlissait un peu. Et puis, quand Sylvie a dit qu'avec Annie Miel, tu avais accepté dans leur bureau parce que tu étais bien roulé, là j'ai vu Cyril Marzouk sortir d'une boîte de chocolat une seringue qu'il a plantée dans le cœur de Vincent, d'adrénaline. Donc là, je me suis dit, bon, pour mes blagounettes, je vais peut-être aller voir Grégory avant pour voir quelles sont mes marges de manœuvre. Donc, j'avais écrit un texte un peu long. Et puis, je le tends à Grégory. Et là, je vois, il s'agrippe au truc. Il commence à dire. Il avait l'air stressé. Alors, je lui dis, je n'ai pas parlé de tout. Toi, par exemple, je pourrais parler de. Enfin, tu sais, tu te souviens. Là, ça en est où d'ailleurs? Moi, on ne me dit plus rien. Donc. Là, Grégory, il me rabaisse, il me dit, non, mais là, il est hors de question que tu parles de ça. Hein. Je veux dire, les Suisses nous l'ont prêté 1 semaine, hein, et le contrat de Swiss Life est très clair. Hein. Donc, physiquement, intellectuellement, et surtout sa réputation, elle doit être la même avant qu'après. Concernant sa réputation, il ne table pas sur une amélioration parce qu'on est en France, mais quand même, je veux dire, c'est exactement, il ne peut rien arriver. Donc, ils sont très stricts. Concernant les anecdotes, par exemple, une oratrice voulait dire qu'il se couchait très tôt, hein, et ils lui ont dit, d'accord, mais à condition que vous vous dites qu'il se lève très tôt. Alors là, ça a tué complètement sa blague, donc ça ne marche pas du tout. Bon, et puis ensuite, ils l'ont autorisé à aller à Orsay un après-midi pour une soutenance de thèse. Et donc, avec le surplus de l'entretien des jardins de l'Université de Zurich, ils ont réparé la ligne B du RER. Hein, oui, alors là, évidemment, bon, quand Amaury a appris ça, il a fait la gueule parce qu'au régional, il a voté Pécresse pour rien. Mais bon, donc, alors je dis, mais quand même... Enfin, je sais pas, il y a le passage quand même où je dis que, franchement, ces articles merveilleusement clairs, moi, quand j'ai été étudiant, ça m'a permis de comprendre des choses en fait très compliquées. Puis aussi, je sais pas, sa contribution à la théorie des processus de Lévy, les fragmentations, les processus de croissance-fragmentation qui se retrouvent au cœur maintenant d'énormément de probabilités d'aujourd'hui. Et puis, il n'y a pas que ça. Aussi, c'est quelqu'un de très généreux avec ses idées, en plus d'être un collègue d'une grande gentillesse. Je pense qu'il y a plein de gens au Congrès qui lui doivent beaucoup scientifiquement, mais pas que scientifiquement. Et donc, là, tu t'arrêtes tout de suite. C'est pas possible. Je veux dire, essentiellement, toi, d'habitude, tu dis absolument n'importe quoi. Donc, c'est quand tu manges un yaourt aux fruits industriels où il y a des vrais fruits dedans. Enfin, c'est jamais vrai. Hein. Donc là, tout d'un coup, si tu prends un yaourt comme ça et que tu mords dans un vrai fruit, ça te rend nerveux. Hein, donc, il va pas être content, il va être agité, il va se demander ce qui se passe, ce que tu lui veux, s'il y a un piège, si tu te fous de sa gueule. Bon, bref. Donc, c'est pas possible, tu peux pas faire ça. Hein. De toute façon, on va remettre Jean samedi à l'Université de Zurich sur le port franc de Zurich. Il y a un état des lieux, hein, et ils lui ont mis un holter tensoriel. Hein. Donc, c'est simple, quand maître Schweinhammer, il n'est pas commode, il va avoir un pic au moment où tu vas dire ça, c'est pas possible. Donc, tu me donnes ton texte. et je te le rends. Et voilà. Bon, alors, donc Jean, excuse-moi. Excuse-moi, voilà le texte. Donc voilà. Donc, voilà. Bon, là, c'est un peu bouffon, hein, cette con. Le contexte était très différent. Hein, et là, voilà. C'est pas fini parce que j'ai quand même un peu négocié. Et voilà, mais le deuxième, j'en voulais 3, mais ils m'ont dit non, c'est pas possible. Bon, sorry, I switch back to French. C'est simplement normal. And now something completely different. So I will speak of scaling limits of tree-valued branching random walks. So it's a joint work with Robin Canfir, who is in PhD with me, Shen Lin from here, and Nicolo Tori, who is now maître de conférence at Nanterre. And so I will consider branching random walk that takes their value in actually deterministic tree, B-regular tree, that I will view as a set of finite words that can be written in with B distinct letter that I will take as a number from 1 to B. And the empty word is the origin of this tree, of root. And I view this graph, this set of words as a graph, and equipped with the graph distance that is given here. So it's just a number of minimal number of vertices joining two vertices in the tree. Okay. So here I will also consider a simple random walk on the B-regular tree. So a population that moves according to this spatial motion. And so we think of a particle that starts at the origin. And when it is not at the origin, then it goes down with probability 1/2. So it jumps to the vertex that is closer from the origin. And with probability 1/2, it goes up. And when going up, it chooses one of the B neighbors of the current position. So it's and at the origin, then it's just a reflection. It just goes up with probability 1, and it picks uniformly at random one of the B neighbor of the origin. So this is the null recurrent Markov chain, the null recurrent simple random walk on the B-regular tree. And then I will first speak of instead of immediately looking at a branching random walk, I will consider just the trace of one single non-branching random walk in the tree. So I'm looking at the successive position of this particle, x0, that start at the origin, x1, etc., and up to time n. And then we have a random subtree of the B-regular tree. And the problem I will first consider is the scaling limit of this random subtree of the B-regular tree. So by scaling limit, I mean that I want to rescale the edge length of this graph equipped with the graph distance. And then I wonder if there is a limiting object, so a limiting random metric space. So the limiting space has to be a continuous, in some sense, space. So and the analog in a continuous setting of tree are real tree that I will introduce briefly here, because most of the people here already know many things about that. So a real tree is thus the analog in continuous setting of graph, tree graph as graph, sorry. And so it's a connected metric space where any pair of points can be joined by actually a continuous injective path that turns out to be geodesic. And so a real tree can be, in other words, constructed by gluing together intervals of the real line without creating cycles and equipped with their own topology. So among metric spaces, real trees are characterized by, among connected metric spaces, real trees are characterized by 4 points condition. So that is written here. It's a purely metric condition. And in what follow, I will only consider compact real trees. And I will equip real trees with 2 additional features. So a root, that is a distinguished point, and also a probability measure. And I will speak of, it's a bit heavy to say, measure rooted compact real trees. Okay. And since so first, one important example to yield a real tree is to produce real tree thanks to continuous function. So here I look at a continuous function C that is continuous and defined on the interval 0, 1. And then we view this function as an exploration of a real tree that is topologically embedded in the oriented half plane. So the root is on horizontal axis. And then we explore this tree continuously from the left to the right. And C of t is just the distance from the root through the exploration. So with this picture in mind, so I don't know if there's no, oh, sorry. Okay, so with this picture in mind, so the common ancestor of the vertices visited at time s and at time t is at the minimum of this function, and so the distance is these functions above. Okay. So this is actually a function that satisfies a 4 points condition, and it's therefore pseudometric, and it yields a metric space when we take a quotient with respect to the zero distance equivalence relation. And I keep denoting the same way the distance it yields. And then the application that gives you the point in the tree from the real, that is the time of visit of this point, is continuous, and therefore this metric space is compact, connected, and since the distance satisfies the 4 point condition, it is a real tree. So the root is the equivalence of 0, and I equipped this tree with the mass measure, that is the measure induced by Lebesgue measure on the tree. Okay, so this is one example of one way of producing real tree. So here is a picture. So we see the function here, and actually it is the distance from the root of a continuous but not very complicated tree actually. And then, as explained by Christina, we put glue under the graph here, or we suck the air below the function, and here we make the tree appear. It's less beautiful than in Christina's talk, but you know, I entirely rely on colleagues to produce such cartoons, so I'm really sorry. Okay, so we want to pass to the limit for a tree. So there is one way to define a suitable space for tree. So we consider 2 rooted compact measure real trees. And we say that they are isometric if we can find a surjective isometry from one to the other that preserves roots and also the measure. And the space of tree I will consider are up to isometry. So it's T, the set of isometric classes of compact rooted measure real trees. And we can equip this set space with the Gromov-Hausdorff-Prokhorov distance. And actually, so it's given by this big infimum. So formally, when the Gromov-Hausdorff-Prokhorov distance is small, so it means that you can find some big metric space and embeddings of T1 and T2 in this big metric space in such a way that they overlap in some optimal way with respect to the Hausdorff distance on compact subsets of on E. and in a way that such that the measures are close with respect to the Prokhorov distance, and we want also control on the respective roots of the embedding. So in the case of Gromov-Hausdorff distance, so without measure, Evan, Pittman, and Winter has proved that actually it's a distance, and that this space is Polish, and Abraham, Delmas, and Oscheit extended this result to this Gromov-Hausdorff-Prokhorov distance that take into account the measure we equipped the trees with. Okay, so actually we will pass to the limit in a more tangible way that I explain now. So we will have a sequence of compact real trees and some exploration, continuous exploration that is denoted by P of n. So it's a continuous surjection from the interval 0, 1 on to T of n. And we equipped, as explained, the tree T of n by two things. So a root, that is the first vertex, the first point visited at time 0 in this exploration, and the probability measure on Tn induced by the Lebesgue measure. And actually, if we prove that as a process with a double index S and T in 0, 1, given by this distance, converges uniformly on the space of continuous function on 0, 1 with the uniform norm to a limiting distance process, then it implies that these sequences of trees converges in the space of tree equipped with a Gromov-Hausdorff-Prokhorov distance. And actually, we have a very simple control of this distance in terms of this matrix. And I explain that because in what follow, we will consider trees that have no clear contour. So we have to do things a bit differently, proceed a bit differently. So here is the first result. So I just consider one single random walk. So and the trace, so the T of n, and we can prove that when the edges are rescaled by a factor n to the power 1/2, then the distance of the position of the random walk at time n times s, n times t. So here I take a continuous interpolation of this random walk. When it converges to a limiting pseudo distance dc of s and t, that is generated by a linear Brownian motion reflected at 0 up to time 1. And so actually it implies a convergence for the trace Tn with the metric rescaled by a factor n to the power 1/2, and the occupation measure here, and it converges to the mass measure, so the tree coded by the continuous function C, and also equipped with the mass measure M of C. So the convergence holds weakly on the space of tree equipped with the Gromov-Hausdorff-Prokhorov distance, and T of C is a variant of the Brownian CRT. So in supercritical but near critical cases, I've already proved a result like that. So with a slightly different result for the measure. So there is a local law of large numbers here for the empirical measures. And in a random environment, when T B, so the B regular tree is replaced by a Galton-Watson tree, so the distance from the root converges to reflected Brownian motion. So it has been proved by Perez and Zeytouni in 2008 for one type Galton-Watson tree, and by Dembo and Soon in 2012 for multi-type Galton-Watson trees. So in random environment, the convergence of the trace as a metric space has been proved by Duquesne and Dora Feliz in 2017, and there is a new proof by Robin Canfier in 2019. Okay, so let's go back to the main problem I want to speak of. So here I will consider branching random walk and the indexing tree. So it's random walk indexed by a random tree, tau of n, that is actually distributed uniformly on the rooted order tree with n edges. So we view this random indexing tree as a family tree of a population that moves in the B regular tree, that is the space where they evolve here. So the root row of tau of n is viewed as the ancestor of the population. Okay, so I will first speak of the scaling limit of this uniform tree. So it's something that is well known. So we can, for instance, look at the contour of this tree. So we just think of a particle that comes from the root of tau n and then visit from the left to the right this tree. So as in the picture here. So it crosses twice each edge. So once upwards and once downwards. And the total travel time is twice the number of edges, so 2 times n. And the contour process is in green here. It's just the distance from the root through the exploration. So we all know that actually this is a variant of the excursion of symmetric simple random walk on Z, and it converges to the normalized Brownian excursion that can be seen, for instance, as the normalized excursion of a linear Brownian motion that straddle time 1. Okay. And so of course, everything is translated in terms of tree. So tau n, when the edges are rescaled by a factor n to the power 1/2 and equipped with the empirical measure, normalized empirical measure, converges to the tree coded by the normalized Brownian excursion, that is Haldus continuous random tree. And here is a picture of the CRT, and maybe some students of Serge Haroche that want to put in a Lacanian perspective everything may think that it is a deterministic object because all the participants to the conference, or almost all, have used the same picture, you know, with a gooseneck here. So I'm really sorry, it's actually a random one. Thanks, Igor, for your beautiful picture. So it's remind you briefly, it's a random compact real tree, and the mass measure has no atom, full topological support, and the leaves are dense, and branching points are binary, and it's a fractal object of Hausdorff dimension 2. Okay, so it's a known stuff. And so let's go back to our branching random walk. So here, the indexing tree Tn is, as already said, is a family tree of a population that moves in the B-ary regular tree. And so the spatial motion follows a null recurrent random walk on the B-ary tree. So it means that when an individual U, when we know the position of its parent, then it picks at random from the position of its parent a new position according to the transition probability P that is specified above. So here I have here is the probability of the spatial position of the random walk conditionally on the indexing tree. And the main object I'm considering is the trace that is denoted by R of n. So all the position of this branching random walk as a random subtree of the B regular tree. So the question is to find a scaling limit for such a random tree here. And I will first quickly explain what can be the scaling factors epsilon n. So here it's quite simple to guess. We just take a uniform random individual in the indexing tree, un, and so the distance from the root in the indexing tree is something that is of order square root of n, and actually we can be more precise, it converges to some non-trivial random limit when it is rescaled by square root of n. And actually, then we notice that the spatial position of this random individual in the population, if we look at the genealogy, then we look at the distance from the root of all the ancestors on his on the list of his ancestors on his lineage, and so it's just a simple symmetric random walk on Z. So the distance from the root of the spatial position of UN is the absolute value of a simple symmetric random walk on Z. And when it is rescaled by 1 over square root of dn, it has to converge to a standard Gaussian random variable. And so the scaling factor has to be n to the power 1/4. Okay. Then I will extend this remark that the distance from the root of the whole population in TB is actually also a branching random walk, but it's a branching random walk in Z, and actually it's the spatial motion is very simple. It's just the simple symmetric random walk on Z. So it means that if I denote the distance from the root of all spatial position by y of u to the power here, then the jump from the position of the parent are IID Bernoulli random variable with probability 1/2 to be +1 and probability 1/2 to be -1. Okay. So now I will explain, sorry, the main idea to analyze what could be the metric, the limiting metric for limiting space. So I will denote by UV the shortest path in the indexing tree tau of n between U and V. And so I will draw a picture, I'm sorry. So the current position is here in TB here. Then along this path between in the indexing tree, then you have many successive positions like this, but at some point you are at a minimal position, and then you go up like this, and then at some point you go towards V of P. And so here, what you can prove is that when you go down and then you go up, when going up, you take the same path, but not for a long time. It is at most a geometrically distributed random variable. So that's what I have written here. So in red, here is the minimal distance from the root of all the spatial position of individual on the geodesy between U and V, okay? And then in red here is simply the distance that we can obtain by just here going down from here to here, and here is the minimum. Here is the minimum mu of V. And then the difference with the actual distance in the BRE tree is just bounded by something that is, that of course depends on U and V, but is not very big. Okay. And so in some sense, we can say that the whole set of distance of spatial position is very close in distribution to what we can obtain by this one-dimensional branching random walk with the same indexing tree that I denoted by Y, because here in red, we have something that is just the distance from the origin. Okay, so now we can already guess how to define some limiting space. Okay. So I will just now define the continuous analog of Y of U, so the one-dimensional Tn index random walk. And so if it's the integrated super-Brownian excursion, and so if I fix two vertices in tau n that are distinct, so the difference between Y of V and Y of U, so it's just a sum of Bernoulli +1 -1 with probability 1/2 random variable. So and how much? So exactly the length of the geodesic between U and V. So it is approximately square root of the distance in the indexing tree between U and V times the standard Gaussian random variable. And this leads to a way to define what could be the analogs in continuous time. So here it's we consider the Brownian CRT, so encoded by the normalized Brownian excursion E, and on this tree I will define a Gaussian process, a real valued centered Gaussian process Y of sigma, whose covariance is characterized by this. It's actually what we could define as a Brownian motion on the Brownian tree. Okay, and of course I take a regular version of it. So Y is the one-dimensional integrated super-Brownian excursion, and it appears in many talks this morning and this afternoon probably. So I won't speak too much of that. And so here is a representation of this integrated super-Brownian excursion. But here, Jean-François Marker has added a small drift to see something. Okay, so it's not really an exact picture, but we can see how it works. So on the horizontal line is the space where it lives, so the real line. And here we have another picture by Jérémy Bettinelli, where we can read the value of Y on the vertical axis. And here the green shadow is the Brownian normalized excursion that codes the Brownian tree. Okay. So then we can define exactly as in the discrete case. So it's recalled by the fact number 2 above. We can define a possible metric, okay, for the limiting object by mimicking what happens in the discrete case. So here I consider the time S. It corresponds to a vertex in the CRT, S tilde. So it's and then for 2 time S and T, I will define the cactus distance ds of t as the absolute value of y at the vertex S tilde plus y at the vertex in the CRT T tilde minus the minimum of the value of the integrated superbrownian excursion on the geodesic that joins S tilde and T tilde in the continuous continuum random tree. So we can prove actually that it is a pseudo distance that satisfies the 4-point condition. And so we get a true metric space by taking the quotient with respect to the zero distance equivalence as usual. And the limiting metric space that we obtain here is a variant of the Brownian cactus that has been introduced by Nicolas Curien, Jean-François Le Gall, and Grégory Mirmont in 2013. And that we call here the reflected Brownian cactus, because here we take the absolute value at some point, but it's not so important. Okay. So to make a difference. And we equip this metric space, so the reflected Brownian cactus, with, of course, a root that is the equivalence class of 0 and an occupation measure. So that is the measure induced by the Lebesgue measure on 0 and by the equivalence class here, okay, as in the Brownian tree. Okay, and so here is a picture by Jeremy Bettinelli, that not exactly the reflected Brownian cactus, but we can prove that it has been proved by Nicolas, Jean-François, and Grégory that it is a random compact real tree, and of course the occupation measure has no atom and full topological support. The leaves are dense, and all branching points are binary, except perhaps except the root, actually, because of the reflection. And it's a 4-dimensional fractal object, but it has no clearly tractable contour process to code it. In particular, the 1-dimensional snake is not the contour of the tree. Okay. And then here is at least, at last, I should say, the result that we got with Nicolo, Chen, and Robin. We can here, for any time S, denote by UN of S the vertex in the indexing tree visited at time 2n time S, when you explore by the contour function the uniform tree tau of n. And then the family of distance here, when it is rescaled by a factor 1/4, converges to the cactus distance that I have introduced just 1 second before. And then we can also prove it's a byproduct of this convergence that actually the range of the branching random walk with h is rescaled by n to the power 1/4, and the occupation measure of the random walk converges to the Brownian cactus weakly on the space of tree equipped with the Gromov-Hausdorff-Prokhorov distance. But we have also a law of large number, so we can prove, for instance, that the number of points in the range divided by n converges to strictly positive constants in probability. And more precisely, we have a local law of large number, so we can look at the empirical measure of the range of the branching random walk, and we can prove it asymptotically converges in the Prokhorov distance to C times the occupation measure. And actually, it's not so simple to prove that. It is much more simple to prove the limit for the distance than to prove this local law of large number. Okay. So we have finally a complete picture, so and a convergence for the empirical measure and rescaled version of the trace of branching random walk. So spoiled. So I would like to conclude, to make a few remarks. And so all the convergences I've mentioned before hold jointly with the convergence of the CRT here. And of course, the law of large number uses several arguments that we can find in the paper by Jean-François and Shenlin, who considered the ZD valued branching random walks. And as in their paper and as in the more classical setting of simple random walks, a constant C can be interpreted as a probability of not returning to the starting point for an invariant version of the branching random walk. So we use here subadditive ergodic theorem. So, and all these results can be extended to indexing tree that are Galton-Watson tree conditioned to have n edges, and also was offspring distribution can have an infinite mean and being in a domain of attraction of a stable distribution. So here the limiting indexing tree are stable CRT, and then we can define stable reflected Brownian cactus. So there's no special problem about that. And I would like to mention that the convergence for the metric uses result for snakes. I mean, convergence results for snakes, discrete snakes that are due to Janssen and Markert in 2005 in the Brownian cases, and to Cyril Marzouk in the other stable cases. Okay, so I will stop here. I don't know if there's something. Much too fast, I'm sorry.
So thank you, Thomas, for a very nice talk. So we have plenty of time for questions. So we have a couple over there.
Okay, so you consider your random walk with values in the B-regular tree, but of course it would be natural to take instead of the B-regular tree and also supercritical Galton-Watson tree. So have you thought of that?
Yes, it's an ongoing project with Robin Canfir, actually, and a variant of that. Yes, but it's the law of large number should be okay, although it's much more technical than we thought before. And the metric problems are a bit complicated too. So actually, it's much more difficult than expected.
Okay, thank you.
Thanks, Thomas, for the beautiful talk and for the beginning as well. First question. So this Brownian cactus, so you have a vision, the integrated super Brownian excursion with the Brownian motion on the CRT, but it is also the Lamperti transform of the 3-half stable gross fragmentation tree associated blah, 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 blah. So the same as I was describing in the end of my talk. And so could you take a gross fragmentation perspective by imagining a kind of local time of particles which are, climbing up, going upwards at some point and never coming back to this point, and counting this as a local time and have a joint convergence to the Brownian cactus with the local time, which is given by the perimeters at the heights in the.
So we thought about that, but it's quite difficult. Yeah, but not impossible.
Okay,
but I have no.
If I may ask a second one, so going on in the same vein as Jean-François, so if you now consider an embedding of your branching on the MOOC, but in a spherically symmetric tree of polynomial growth, then I guess that the picture that you have on the left-hand side, you have a common part. And so you should have the Brownian cactus, in which you collapse some branches, but you still have a tree because the common part is strictly
Actually, we have some, well, you can do that picture it holds true in tree where you have infinitely many, in a space where instead of B neighbors, you have infinitely many neighbors. Okay, so there is no problem here. And then you can contract things. And
Yes.
so the idea is to, and so you can do it in a very regular way in this way, or of course you can vary according to the level. It's quite possible to do that.
Thanks.
Thank you.
So if you, instead of considering the regular tree you started with, you take a graph which is close to be a tree, but which has a few loops from time to time. So how robust are this type of result you get? I mean, probably they stay true up to a certain point.
Well, already for one single random walk, there are results, of course, and so you can look at in hyperbolic spaces. I mean, continuous something like that, and look at that. So Gregory and Xing Shen, where is Gregory? Look at, for instance, for one random walk that turns back to its origin, the limit, and then show that when it is suitably scaled, it converges to the Brownian tree. So we can do that, of course, with branching random walk version of that. But the problem is you have to go back to the origin or to impose something on your branching random walk. But it is perhaps possible to look at discrete version of graph with that are hyperbolic in broad sense, but I've not considered this question carefully.
Okay, so I'm going to transmit a question from Arthur Blanc-Renaudy, who can't use his mic. So, is there any way to naturally define a random walk on a tree directly from its height process?
So here it's when the tree is regular, it's quite obvious. You have the height process, and when you choose when you go up each time, and so you have something that is quite tractable. But when you're, for instance, when your environment is random, like Galton-Watson tree, it's something that is much more complicated to do that. So the answer is.
Are there other questions? Doesn't seem to be so. So let's thank Thomas again.